I would like to talk a little bit about the materials genome. So, yeah, when I was looking at this list of titles, you may got the feeling. My background is chemical engineering, not math. And of course, I don't want to even assume that you are all thinking that having skills in topology data analysis is equivalent in bringing a duck to a lecture hall. But I do want to emphasize that this is work done together with Paweł Droszko, who is an expert on these type of techniques. So before I forget, this is work we have done with many people. I can't name them all individually, but you see the names appearing. The materials genome, that is something that originated in the US, and I will explain the title a little bit later. It was on the web pages of the White House. Of course, you have to look in the archives of the other administration to find it again, because this is science and that's not that popular anymore in the US. But the idea is, and that is something, if you have a new material, it can take many, many years before you see that in applications. And then the question is, can you use computational techniques to speed that up? And that is sort of the idea of this materials genome. So let me first start with the nanoporous materials where we are interested in it. So it becomes a little bit more clear why this genomic approach doesn't completely sound as nonsense. So this is the material we're interested in. It's called a metal organic framework. And what is characteristic? It's a crystalline material, it's a powder. And molecules can absorb in these channels you see here. So here there are metal nodes. They are connected with a linker, and these pores are of molecular diameters. So what you can do is you can, for example, absorb certain molecules in there. So if you have a mixture of, say, CO2, carbon dioxide and nitrogen, which is, for example, for flue gases, you would like to selectively remove the carbon dioxide. Well, this is a material you can use. It selectively can absorb CO2. Then you can remove the CO2 from flue gases. That is a particular application. So what is then the interest here is these materials have the world record in surface area. If you have a gram of material, it has a surface equivalent of a soccer field. And what we will see, there is an extreme chemical tunability. And that is sort of shown here on this slide. So the idea is you have a metal node, which is the purple here, and you connect it with a linker. And this is organometallic chemistry, so they coordinate with these oxygen, hydrogen, these parts. And what you see is this is one example of a linker where you functionalize it with different chemical groups. And each of those are new materials. You can have different nets, ways of connecting these to the metal nodes. And you can also change the metal side. So if you then make a back of the envelope calculation with these very simple ingredients, you just put them together and make them, you can make many millions of possible materials. And that is sort of this idea of this genomic. With the same chemistry, we can synthesize many millions of materials. And then the question is, of course, which one is then the best for a particular application? So in my group, we also synthesize these materials, and we actually have a robot for doing this. But just to give you an idea, if we have an idea of a linker and a metal, it typically takes a few weeks to find the right synthesis conditions. And that basically means you need to find a solvent mixture where you get the right crystals. Well, if you can make them, say, over a period of 2 weeks, you need to characterize them, you need to measure all kinds of things, and it typically means that of the order of 10 materials a year we can synthesize and characterize, which is only a very small fraction of the total number of materials that are available. So what we also do is, in parallel, is develop a computational approach where we, in silico, try to generate these materials and try to predict the performance. And as you will see, I will give a particular example, and then I will switch towards where this field of topology and where we needed Paweł's help. So this is this is then the idea. So what we do is, yeah?
May I ask you a very stupid and basic question? These linkers, I mean, is it the length is strictly bounded? So you've got only this very small number of possibilities?
Oh, no. You can add 2 of those, or 3, or 4, or 5.
All right.
So there are about 30,000 commercially available linkers, with all different variants.
Okay.
Yeah. And then you have one where you actually have 3 legs, and then you can form a different combination of those kind of things. And then you can use mixtures and those kind of things. So there are a very large number. I have been warned not to use infinite here because. And please ask questions. I'm giving an audience. Yeah.
So are we talking about covalent or non-covalent interactions?
These are non-covalent, but they do exist in the covalent form. But then they're called COFs, covalent organic frameworks. But the basic. So chemists are very creative in making all kinds of materials, and we'll see a few examples of them. So what we then try to do is basically use these nets, use these building blocks, and here you see them with 3. And we basically enumerate all possible crystal structures. And then we generate the crystal structure in silica. We use quantum chemical techniques to optimize the structure, and this is something we call a predicted structure. And we have them for metal organic frameworks, for polymer porous networks, for zeolites, for ZIFs. There's a whole family of nanoporous materials which are used in different applications. And we have about 3 million of these hypothetical materials. And just to give you an idea, of the order of 5 to 10,000 have been synthesized. Just to give you an idea. Okay, so we have the crystal structure. And what we do then is we use molecular simulations, and that is sort of my own expertise, to try to predict thermodynamic and transport properties. So for example, we try to predict at which pressure, at a given pressure, how many, say, CO2 molecules are absorbing in these porous materials. And what we do there is we basically use a force field. We try to estimate the interactions of these gas molecules with the frameworks, to try to, well, basically we make a flight simulator for molecules. So if you simulate sufficiently long the movement of these molecules in the pores, you can predict thermodynamic properties. And we'll see some examples. So the recipe is, we make the crystal, we optimize the crystal using quantum chemistry, and then we use these molecular simulation techniques to predict experimentally measurable properties of these materials. And that should be sufficient to make predictions on the performance. But let me just give an example on what we tried to do. And this one was extremely successful, but just to give you an idea what we do. So here we try to predict variants of a material which we call MOF74. And it has this hexagonal structure, and what you see here is we try to predict different linkers which you can add to these nodes. And what you can already see, you have to, so there are databases of, say, 30 million known chemical structures. So what you need to do is you need to filter those databases for having approximately the right geometry, that those OH groups are at the right size. And then you can sort of see whether you can synthesize this material. So we predicted this one, and then subsequently in my group, they synthesized the material. It looks like this. And just to give you an idea of how we predict the properties, so here you have pressure, and here you have loading. So what we measure is we have the powder, we put it on a balance, and we increase the pressure, and we measure the weight increase. And that is because it's absorbing. So what you typically see, you get an initial slope which is linear, and then it saturates. And so the lower curves are the experimental data, and the upper curves are the predicted results. And this is predicted before the material was synthesized. It's actually quite good, because it's very difficult to make a crystal as good as on a computer, because we have a perfect crystal, no defects, no solvents that rest. So we're always overestimating the loading. But you see in the low loading, we actually predict the material quite well. So this is an idea. Some of the other materials we predicted, but they have not been able to synthesize. So it's not always like this. So okay, let's now discuss an application, and then I will move towards things that will interest you hopefully more. So it's methane storage, and this is everything to do with energy. And when this was sort of started when I was in the US with this fracking boom. So the US has a lot of natural gas, and the question is, can we use natural gas to drive cars, and that instead of gasoline? That has an advantage that the CO2 emissions are less, and that is also locally found because of these fracking booms. But what is the problem? If you look at 1 liter of natural gas, this is the energy density, and this is the energy density of gasoline. So you see, you need a lot of balloons to drive your car the same distance. So the issue of natural gas is, can we increase the energy density to something that is comparable to natural gas? And then there are two strategies. That is liquefied natural gas. You cool it to liquid temperatures, 110 Kelvin, and that is often used on sea transport, where you see these big bowls of on ships, and they contain liquefied natural gas. Or what you do, you can compress, and compressed natural gas is something that is available, but there the biggest disadvantage is it occupies most of the trunk. So because you need cylindrical tanks that are cylindrical because of the high pressure. So the question is, can we use such a nanoporous material, so a nanoporous materials that absorbs natural gas, but at a lower pressure, 65 bars, and in that way you can fill your tank at home. You don't need a big compressor, and with a pressure which is sufficiently low that you can use a conventional gas tank for that. And if you look at your gas tank in your car, it has a very irregular shape just not to occupy the trunk. So the idea is, can we find a material in which the energy density is the same as compressed natural gas? And that was something which the Department of Energy sent out a call, and a large fraction of the chemists in the US were actually trying to synthesize these materials to meet the targets. And the target is called the deliverable capacity, which is basically the amount of energy which is stored between the high pressure and the low pressure. You have a minimum low pressure because if you need to start your car, you need some flow to start your engine, so it cannot be zero. Okay, and then the question is, can we find such a material? Well, you can do some theory, you can make some simple arguments. So here we have, again, these loading curves. So here we have pressure, here we have the methane loading. So this is the high pressure, where you fill your tank. This is the low pressure, where we decharge, when it's empty. So you see here a difference, the difference between those two. That is the deliverable capacity, and that deliverable capacity needs to be equivalent to compressed natural gas. That's the energy density. And now you already see that this is sort of the ideal curve. Those curves, so here if you look at the initial slope is a measure of the strength of the binding of methane to the material. If this binding is too weak, you don't get a very high loading at high pressure. But if the binding is too strong, as in this case, you don't get it off. So the synthesis is all about making adsorption sites that are just right, not too weak, not too strong. And people have done theory because you can show, if you have such a curve, that's a Langmuir isotherm, there's only one parameter, and you can express that as this. In here you have the heat of adsorption, that's the measure of the energy. This is an entropic term, and they analyzed some data, and then they concluded 16.2 is the optimum slope. However, they analyzed this for only a few materials. So the first thing you can do is you can sort of say, we have this database, let's see whether this is correct, this number. So we did this for zeolites, and just to give you an idea of how well we can predict these adsorption isotherms. So the dots are the experiments and the lines are our simulations, so we can predict the performance of one of those materials. So we have a database of 100,000 of these zeolites, also hypothetical ones, and we can sort of see whether the optimum one is has this energy of has this 16.2. Well, this is what we saw. So what we did is we calculated this adsorption isotherm for every single dot, which is a material. And you can sort of see there is nowhere where you can see this optimum. And that was sort of puzzling for us. But there's also, so this is one class of materials, which is zeolite, but we had databases of many other classes. And what we then tried to do is we tried to see whether one of those materials was actually meeting these DOE targets. So in this way, we didn't get very popular, because what you see here is basically we can't get to the targets. So what you have here is the saturating loading, and here you have the fractional deliverable capacity. So recall that in these, we had this isotherm where we had an optimum interaction. Well, that optimum interaction is the yellow line, but here we basically say this is the fractional deliverable capacity. That means if you look at a site, that site is only fully used if the pressure is 0 at low loading or infinite at very high loading. So you have a theoretical maximum because always some of the material will stay. And this is this theoretical maximum. And here is the number of sites we have in the material. So what you need to do is you need to create an optimum site, which is the yellow one, and that as many as possible. So here, this is a line, which is basically an empty tank. So here you would say you have a material with optimum site, but not that many. Here you have a material with lousy sites, but many of those sites. So this is the deliverable capacity. So every dot is a material, and this is the DOE target. So, and this is the best material we could find, which has a deliverable capacity in DOE units of about 200. Well, the target is 350. So, and this is basically an enumeration of all the current chemistry we know about these materials in this materials genomic approach. And we say, based on our conclusions, you can get to 70% of the target, but not higher. If you want to go higher, you need to do something completely revolutionary different. And we don't think that exists there. But why are the materials above the optimum line? And that is, it's not only important that you have the optimum methane wall interaction, but also methane-methane interaction. A methane molecule can recruit another methane molecule, and then you can get above this limit. But that is a detail. So here we used an application in which we didn't discover a material, but we basically said to the experimental people, you have already the best material, and that's here. So stop further trying, just develop the materials you have. But there are also a few sort of interesting questions, and that is the following. In particular, in these zeolites, the chemistry of these materials is the same, but the only difference was the structure of the pores. And then we actually had as a question, if only the pore shape matters, then materials that look similar should have similar performance. And that it was a question that puzzled me for 7 years without much success until I started to be in contact with this community. So I'm very proud that I can actually tell this work, because this one has been bugging me for many, many years, and I wasn't able to actually even think about this problem in a proper way without getting in contact with this community. So I'm actually very happy that I can report on that. So how to compare? Actually nothing. That is the idea. And that is, of course, a problem if you talk with chemists, because they think everything that matters about them is the chemicals, the molecules they make. And here we argue the pore shape actually matters, but that's not something they can play with. It's not something they have learned to think about. So this is something which is in the chemistry world completely unknown. So how to compare pores? So what you then typically do is this pore mass approach. And that is basically, you look at the material and you think, what kind of descriptors I can invent? Well, that's relatively simple. I can blow a sphere, and what is the biggest sphere I can blow until it touches the walls? Or what is the biggest sphere I can drag through my material? Or what is the accessible volume, surface area, density? You can look at a material and come up with a set of conventional descriptors. And of course, but then you sort of saw our difficulty. So here we use a known zeolite structure. This is SSF, and the blue is the pore shape. So you see it has a three-dimensional pore structure. So we looked at these descriptors, and we identified in our database those structures that are most similar in the sense that they have the most similar descriptors. And you see, we do really well. For chemical engineers, that's not bad. But then the interesting thing is, if you look at the most similar structures, those two, they don't look at all the same. And that was always happening to us. You basically, by accident, this material has the same descriptors, but has no, even from a topological point of view, these are one-dimensional materials, channels, this is three-dimensional, they're completely different properties. So all these approaches sort of failed. So then, to make a short story short, we started to work in EPFL with Catherine Hess and Powell, and we applied the persistence homology for this one. And I needed to tell that the mathematicians were very excited about this, because this was the first application of persistence homology that used the third dimension to get things correct. So what we do is we put dots on the surface, we grow the dots until they touch, and they get these typical fingerprints where you know much more about than I do. But what I can sort of report on you is that these things are actually working extremely well. And for example, here I have the issue which I illustrated before. So here we have a set of similar materials. So here we have the distance in conventional descriptor space, so the pore diameter and all the things we did before. And here we now have a distance in topological space. And that means we use these as a fingerprint, and we calculate distance in this space. We call that the topological space. So what you see here in blue, you see here we do get a reasonable correlation in the sense if the distance in conventional space is large, it's also in topological space. But here you see the problem we had before. These materials have a very large distance in topological space, but have a very small distance in conventional space. So, and that was the issue. So this material was selected as the most similar using the conventional descriptors. So if we now do the persistence homology, you do see we get materials that look the same. And for us, that is already quite something. And the same here, while the conventional space did very differently. And if you then look back at, say, these numbers, you do see that if we use the conventional space, it's a little bit closer in conventional space. But you see, these are not very different, and that is sort of the problem. If you have enormous database, there are always materials that accidentally have the same sort of typical descriptors. So let's now sort of see how we use these methodologies for some very practical applications. And that is, I'm coming from the field of zeolites, and in zeolites there are about 180 known zeolite structures. And every year there are 2 articles in Nature that publish a new zeolite structure. And the community is very excited because they know all 180 structures by heart. So if there is a new one, they say, it looks like this one, because they know it. If you go to the field of metal organic framework, there are about 10,000 structures there. So people have no clue anymore on similarity. So, and this is sort of the most destructive form of science I've ever seen. So what we did, or what my postdoc did, I wouldn't think about doing this myself. He basically said, okay, let's use this topological distance approach to look at all known zeolite metal organic framework structures. Those are the structures I showed in the beginning. There are about 10,000 of these structures, and they published in a database. So what he did is he took every single structure in this database and compared it with all other structures, and then list the most similar ones, but with the following filter. So they needed to be sufficiently similar. They didn't need to have the same name. And they also needed to be on different publications. And the authors did not refer to each other. So what you see here is these are pore structures of authors that are completely unaware of each other's work. And you basically see how badly we needed your help. Because these structures, we have a list of about 25 of these, that all have the same issue. They have pore structures that are very similar, but chemists are very good in comparing similar chemistry, similar crystal structures, but these subtle differences in pore structures they can't pick up. And if you look very carefully, these are not the same chemicals. They are very different chemicals, but they happen to form a very similar pore structure. And here you see already a very simple tool, which we actually would like to promote, is if somebody synthesizes a new structure, they can immediately see whether a similar pore structure has been synthesized. And that is something which is really important we get there. Well, I sort of mentioned this one. Well, this was also something that was bothering us. Why is it we don't see a clear optimum? So this may sound strange, but this article that predicted this optimum has been cited over 600 times. And it's the reference chemists use to find an optimum material. So what is actually going on? So what we then did is we took the top 10% of the best performing materials and then analyzed the topology of these materials. Just so maybe this type of diagrams where the color coding is now the heat of absorption. So what you see is that these materials, if you look at the top performing materials, they sort of separate in very distinct groups. So here you have a group C, this is a typical material, which you see has a relatively high heat of absorption, while group E has a relatively low heat of absorption. So you see with these clustering techniques, we suddenly see, now I get it. If you have a similar material, it has similar optimum heat of absorption. So we can make the following graph. We can take representatives of these materials and then look at similar materials, and you see they peak much better now. Well, if you look at it from a physical point of view, what is actually going on, you have two things. One thing is you have the heat of absorption, but you also have the entropy of absorption. And experimentally, they analyzed only a small subset of materials, and those materials happen to have all the same entropy of absorption. But if the materials are similar, they do have the same entropy of absorption. So in this way, you actually naturally separated materials that are similar, but from an entropy point of view. And experimentally, they were just focused on one group of materials. And that is what you see quite often, that they focus on one class of materials and they optimize locally, and they didn't have this more global understanding of what's going on. So here, being able to identify similar materials helped us to sort of see this problem. Another sort of interesting question, so this one, with this material, the only difference was pore shape. With metal organic frameworks, we said we changed the metal, we changed the linker, and we changed the pore topology. So there, I would argue, if you have similar materials, it's much more questionable whether a similar material from pore shape point of view would be top performing, because there's a lot of chemistry going on. But anyway, we tried. So what we did, and this is a sort of a typical study. So what we did is here are a set of the top performing materials for methane storage. And then we looked in the database of metal organic frameworks which materials have a similar pore topology. And we took the 10 most similar materials to the reference materials. And this was very surprising for us, because this is the deliverable capacity. Around 200 is the maximum. If you're above 150, you're top performing materials. And this is the distribution of the materials of the entire database. So by being able to select the most similar materials, we really in the top part of our distribution. So by simply having a good performing material, by just identifying which one have the most similar pores, you do already have very good candidates. And that opens another very interesting possibility. So if we have a new structure, we upload it, we can upload it, we can calculate which one is the most similar, and we can also say, well, your material looks similar to those, and those have interesting applications in because they are good performing in other fields. So being able to say the similarity, that's already quite interesting. Okay, so another thing we are working on is, that's something I find interesting, is, there's of course now a competition going on who has the best MOF, Metal Organic Framework database, and there are different groups that are competing. And of course the arguments are, we have the biggest, or we have the most number of structures in there. But how do you actually quantify the quality of a database? So what we did here is we also used the topological analysis of the data, and we basically quantified things by using ideas from ecology. What is the most diverse ecosystem? So what but here you already see a few interesting things. So what we have here is, this is the combination of all databases we have, including the experimental one. And the color coding is the number of materials of a certain structure. So this is all the data, and you see you naturally sort of falls into 4 categories of materials. And you see these are groups of materials that have been occurring a lot, and the blue ones are just much more rare. What is now already interesting, I already hinted at, to look at the conventional descriptors, like the surface area, the volume, the density, and the included sphere. And what you already see, if we now look at this color coding, that this topological map nicely separates these conventional descriptors. So on the basis of the topology, we can already say pretty well what the conventional descriptors are. So that is already a nice thing. But what we can do now is we can now compare the diversity of the different databases. So what you now have is, so here is the experimental database. This is a database of one group, and this is a database of the other group. And the gray areas are parts that are not present. So you can already see that this database has a large preference for making materials that are on this side of the diagram, while experimentally there are mainly these type of materials. So what you can sort of see is, you can see certain biases in the type of materials that have been synthesized. And from the gray areas, you can sort of see this database completely lacks these materials, for example. And the other thing is, well, why is this important? Because if you want to do screening studies, what people typically do is they take a random selection out of these databases, because they are too large to look at everything. But if you make a random selection, you will most likely select these materials, and very low probability to have these other materials. So being able to quantify sort of the diversity of your data set, or vice versa, being able to generate a representative set of materials that nicely covers the entire space is sort of an interesting application. So it's the same with zeolite structures. You see they nicely separate with these structures. And if you look here, you have some of the known zeolite structures, and here there's a large fraction of materials that are predicted and have never been synthesized, and they look like this. Okay, so in the remainder of my talk, I would like to tell a few things where we're not that happy with. And so, for example, our techniques are relatively too expensive. So one of the things we do not know very well is how to take symmetry and periodic boundary conditions into account. So what is the issue here? So if this is our structure, so this is the unit cell, you already see you have a mirror symmetry, you have a symmetry here, so we're generating way too many points, but we even do worse, because we would like to compare a material that has the same volume. So what we do is we replicate this 4 times, and we replicate this 2 times, that they have approximately the same volume, and then we put the dots at the surface to calculate the persistence homology. That would be much more elegant to only use the crystallography, that you can use the optimum symmetry. And because of that, the calculations get relatively expensive. So if somebody has a very good idea, that would be beautiful. So there we really do not know how to address this one. There's another problem, and that is, if you look at these materials, the pore shape is dependent on which probe you're using. So let me explain that. So for example, we are interested in the adsorption of methane, as we have seen, but you can also use these materials to adsorb hydrogen. So hydrogen is a smaller molecule. So if you look at this material, you see you have a central channel with side pockets. Hydrogen is small, so it can enter the side pockets. So this material actually looks like this, but for methane it's just a straight channel because these are inaccessible. So the way we solve it is we just use the blue ones for methane, and we make a new one for hydrogen. So for every single application we have different fingerprints. That's not very elegant because we have only one single material. Well, can you do something where you make a fingerprint pore size dependent, so add a dimension to it? That seems to be hard because you lose directionality, and I haven't fully understand the details, but that is a difficult one. So if you have ideas, very interesting. So the other thing, if you have paid attention, so what we did is we put spheres of points for the persistence homology on the surface, and we grow them to make a fingerprint. So from that aspect, this material is completely identical to that material. You can't distinguish a fingerprint. However, the chemistry, which is occurring here in the empty space or here in the empty space, is very different. So the performance of those two materials is not the same, yet they have the same fingerprint. So here our worry is that if you have some characteristics, say of this part, that if it occurs in another one, we identify them as being similar, while they don't have a similar performance. Of course, with screening studies, you're already happy that if you increase the probability of success by a factor of 200, but from a fundamental point of view, we still need things to do. So my wish list here is, the crystal symmetry, the way we do these calculations are not sufficiently efficient, so we can't do it yet for all materials. And in particular, at a given moment, you need to calculate this distance matrix. And if you have a million materials, it gets too long. So we need to use smarter techniques. So a better description, the difference between the inside and the outside. And the other thing is we don't have yet a perfect understanding of how to weight all the different aspects in this. For example, some properties depend more on the global things, other properties, like we have used the material for separating xenon and krypton. There you need very subtle differences in shape. How can you emphasize one and the other? Which distance to use? Can we do these things more efficiently? Okay, so the conclusions are, so on methane storage, so the interesting thing is these screening studies, they do give you a very clear recipe of what you need to do. You need to create materials with the right adsorption site, the strength not too weak, not too strong, with the right distance of methane and as many as possible. So what you then also can sort of see is why do we have this limit? Well, the essence is actually quite simple. if you have a material, you create an absorption site, and it's easy to tune the chemistry that this one has the right energy. That's good. This one is optimum. We create another one. That one is also optimum. And another one. And another one. But at a given moment, you don't have the material anymore to maintain this optimum energy. So at the end, you're creating such a Swiss cheese that it basically, it's the quality of the air that counts rather than the cheese. So you cannot maintain the optimum energy anymore, but you do have many absorption sites. And there you have a compromise. So you need to have some stuff to create a site that is optimum, but you also need to make a material. And that compromise is somewhere, and by this enumeration you can quickly see where it is. The other thing is, methane is not a magic molecule. It has van der Waals dispersive interaction, so there is no chemistry you can play with. So there is no magic with methane. So that's why we strongly think that this is a real limit. Well, of course, then the RPI, which is the energy agency from the Department of Energy in the US, these targets are too optimistic. Although 70% of the target is actually quite good. But if you try to see, it just means that your car cannot drive that far as with 100%. But it's still better than an ordinary gas tank. So better focus on having the material, the materials you have, and see whether they can be turned into an economic model rather than trying to get somewhere where there are no targets. Okay, so with similarity, and that is thanks to Pavel and Catherine Hess, we now really have, we have heavily relied on all your expertise to have a language where we can compare and quantify similarities in pores. And that for us is actually a very big step forward. We can quantify the similarity, we can give people or people that synthesize new materials advice on whether similar materials exist, but also give them suggestions on for which these materials may actually perform very well. Okay, so I've also given you some examples of what we have done with this materials genome, where we try to enumerate all possible structures, and this of course gives all type of opportunity for machine learning and big data. So I do expect from this interaction from the community I represent with your community has many interesting possibilities, and I hope that this is not the last presentation I'm going to give or interaction I have with you, because I think we made enormous progress. And with that, I would like to thank again the organizer for giving me the opportunity, and I hope you enjoyed hearing something from a very different field where they don't think about bringing ducks to the audience. Thank you.